Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so in this last session before the break, I'm going to try to... Okay, it helps if I have the slides. So in this last session before the break, I'm going to try to link together the two topics I was talking about, first of all. The transactional memory API in terms of start, read, and write operations. And then the higher level programming abstractions such as atomic blocks and retry and all else that we'd like to build over that. I'm not sure I'll quite fit this in the time, so I might keep a few of the last slides from this session over until the next lecture in my set. So this is, again, taking some of the work we did in the Bartok STM system. So the code is loosely based on C#, but it would apply to lots of other imperative languages. And what I'm going to talk about is how we would build a language implementation for atomic blocks with this kind of syntax over the read and write API. So this is very similar to the pseudocode I started out with. We've got a queue with some, in this case, some left and right sentinel nodes and a linked list of elements instead of an array, but a similar push and pop left abstraction and the code within the atomic block implemented in much the same way as it would be implemented in sequential case. So to put an item onto the left-hand end of the queue, we allocate a new queue node. We then update a lot of pointers to link that together, making the left sentinel point to the new node that we've allocated and making the previous left-hand node of the list point to our new one. So lots of pointer swizzling, but the guarantee of atomicity and isolation means that we don't have to worry about how concurrent atomic blocks interact. We just have to make sure that this atomic block moves from one consistent state of the queue to another. And we like to allow the program to implement something like that with atomic blocks rather than using the low-level read and write API that the STM system provides. So the basic idea is that we'll have the compiler expand the high-level syntax into a series of reads and writes. So each of the writes to a field turning into a call to a write function on the STM runtime system, each of the reads turning into a read function. And of course, although this is in a high-level language, the transformation here is something that would happen during compilation by a trusted part of the system, maybe the JIT compiler or an ahead-of-time bytecode to native compiler. So, of course, this syntax for direct taking the address of individual fields and making direct accesses in the style that you would in C is something that would be possible in that level within the runtime system, even though it's not something that would be actually expressible directly in the source language like this. The approach we've taken in the Bartok STM system is to put most of the work at this end, so when we're going from the bytecode language into code, and to just have a little bit of support in the source code to bytecode compiler for allowing the programmer to express atomic blocks and to express retry and or else and so on. And the basic motivation for splitting the work like this is that in practice there's very little information loss between the source code and the bytecode. The bytecode still has to be type safe. It's not able to express all the pointer arithmetic and things that we use in the STM runtime system. Whereas if we do this work in the bytecode to native compiler, that can be integrated much more closely with the runtime system. And as I'll say later this morning on the next session, we've also got integration with other parts of the runtime system, such as the garbage collector. And that really pushes us towards working at this later stage during compilation. So finally, doing the work at this later stage also enables a lot of optimizations. I'll come back to some examples of those in a moment. In terms of the high-level language, the extensions that we do are to transform an atomic block into a special kind of try-catch block. So when the source compiler sees an atomic block, it becomes a try-catch with a specially named exception. And that's just a way of expressing in the bytecode language that this is the block structure of an atomic section. It's difficult to add additional constructs to the bytecode language, so this avoids us needing to modify it. And then the bytecode's native compiler recognizes this special try-catch, and that triggers the compilation of the code within into calls onto the STM runtime system. So within one of these try-catch blocks, we're going to do some, first of all, some expansion of the start and end into effectively boilerplate operations on the STM. So we start by repeatedly executing this until the commit succeeds. So at the start of the function, we'll set a flag that's going to say whether we're done with the transaction or not. We'll then try executing it. And if we get to the end, we'll try to commit. The way that we designed the Bartok STM system is that if a conflict is detected, either inside the commit function, or if it's detected, say, when we compete for a write lock within one of the data accesses, then the runtime system will raise a transaction invalid exception. We catch that at the end of this loop, and we just set the flag back to false to say we're not yet done with this atomic block, go around the loop again and try once more. So the actual start and commit are straightforward, and the difficulty then is in expanding the data accesses inside the transaction. The first attempt at this is just to turn each of the reads and writes to a field into a call on the txRead or the txWrite function. So we can do this by a fairly mechanical expansion of each of the bytecodes. There's different ones for accessing different typed fields, accessing arrays, computing various kinds of access. So within the bytecode's native compiler, we recognize each of these kinds of data access bytecodes within an atomic block and expand that onto a call onto the appropriate STM runtime system function. Now, there's a few problems with this basic approach here. One of them is that we'll be expanding a lot more memory accesses than we really need to, because we can see here that we might be reading or writing to the same field multiple times. And we don't really want to be going through this call onto the STM runtime system and doing all of the logging work every single time we access the same piece of data. We might also want to handle thread private data separately, because we know there's not going to be a conflict between one thread and another thread if they're just dealing with thread private data. So again, we can end up accidentally over-instrumenting the code. It's going to run correctly, but it's going to be slower because we've instrumented more data accesses than we need to have done. So what we developed to try to improve performance is what we call a decomposed STM API, where rather than talking about individual read and write operations, we have operations to indicate our intent to read or write to an object or to give an address, and an operation to record a value that we're about to override. So the idea is that instead of having the STM runtime system perform these different steps of writing to the different logs, we will expose these as separate operations exposed by the STM system, and we'll allow the bytecode to native compiler to optimize the placement of these operations to try to keep the overheads of the system as low as possible. So let's look at what happens during the compilation for a couple of examples. The first one is reading from a field. We're reading from a field in object P and storing it to a local variable X. And that will be turned into two operations in the bytecode's native compiler. The first one is doing the logging work associated with reading from the object that P refers to. And then the second operation is doing the actual data access. And then in the second example, we're doing a store to a field in that object. And that turns into three steps in the compiler's intermediate code. One that opens the object for update, which means writing to that updated object log. Another one that is logging the field that we're writing to, so that's going to store to the undo log. And then we do the actual update. And the rationale for decomposing the operations like this is that it gives us a lot of new opportunities for optimizing the code. So in the swap example, we'd start out in the naive code that's produced early during compilation with each of these field accesses expanded to the open call and then the data access. So the two reads here and then the two writes. And then you can see there's a lot of redundancy in this. We're doing the concurrency control for reading an object P twice. So the optimizations going on during bytecode to native compilation are able to eliminate this second read by doing a forwards data flow analysis to check which objects we've already opened for read access. The same is true for these updates, because we know we're updating object P before this first field is accessed, and so we can avoid the extra work on that same object for the second field. Then, in fact, we can notice that we're reading from P and then updating it. And so we can just acquire read access right at the very start of the atomic block, and then that grants us write access as well. And we can eliminate the open for write and the later open for read. So we get quite a substantial simplification. In most of the programs we've looked at, this gets us about a twofold reduction in the overheads of using the STM system to instrument a piece of code. And that's largely by identifying this kind of redundancy where the transaction is accessing different fields of the same object in this system with object-based concurrency control. So the compiled code ends up being substantially shorter. We have the start and commit boilerplate that I mentioned earlier, and then the data is being protected by the calls onto the STM system to do the per object logging before we do the update, and then do the per field logging before we overwrite values in the object. Now, there's a lot of extra complexity here. We need to handle local variables in addition to objects in the heap. We need to handle references to fields that are passed in using the byref features that are in the .NET bytecode. We need to handle method calls. To a large extent, these are there's a lot of details, but the transformations done in the compiler are relatively straightforward. So for local variables, these are accessed in .NET as in Java with a distinct set of bytecode operations to field accesses. And we instrument those in a different way, adding a second local variable to hold the old value, storing into that shadow local variable at the start of the atomic block, and restoring from it if we need to roll back the atomic block. To handle method calls, we duplicate the methods that might be called inside an atomic block and produce an instrumented version of those methods so that we call from if we're inside an atomic block, we call the instrumented version every time. And if we're outside an atomic block, we call the normal version. So that means we can do method calls within atomic block and get this kind of composition that I was talking about earlier. For byref parameters, we have some integration with the garbage collector. So if we're accessing a field indirectly, then the garbage collector provides a mapping from the address we're accessing back to the start of the object, and that then lets us access the metadata for the object. Let me talk about a few of the more tricky cases that are more specific to STM. Here's an example where we've got a somewhat contrived piece of code where we're taking a reference to a pair object, and this tx suffix means that this is one of these functions that the compiler is generating, so that we'll be calling into this version of the clear function if we're using it inside a transaction. Tx suffix there. And then within the function, we're iterating through 10 times and storing a constant value in one of the fields and storing the loop index into another field. Now, if we were to instrument this code in the way I just described, we'd end up adding the code to open the object for update at the start here. We'd do the two accesses to the fields, and then we do the two stores. But we need to be careful because an optimizing compiler might try to hoist this store of a constant value out of the loop, because that's going to be loop invariant, and it only needs to be done once rather than on every iteration. And of course, now that perfectly reasonable looking optimization has broken the use of the STM. We're accessing the field here before we've opened the object for updating and before we've logged the value that we're overwriting. So we need to be careful about how the transformations we add for STM are going to interact with the other transformations that the optimizing compiler might do. Yeah. Mm-hmm. The question is what actually needs to go on when we call this open for update primitive. What we do in Bartok STM is this open for update is the steps on the slide I had before the break, where we were looking at the version number in this object and recording that in the opened objects list, the right set. So this is going to involve probably about a dozen machine code instructions that are finding the version number for the object, allocating a new slot in the log, and then writing that version number into the new slot. So it's going to involve the read of the version numbers as part of that. Now, what we do to keep optimization safe and make sure that other parts of the compiler don't break the atomicity or isolation that we want is to introduce some false dependencies between different instructions in the intermediate code of the compiler. So these temp1 and 2 variables are present at compile time, but then don't have any runtime component associated with them. And they're used to add data dependencies between the different steps of the STM's work. And then these data dependencies constrain what the optimizing compiler is going to do. So conceptually, we have open for update generate a value that we store into temp1. Log for undo consumes as an additional input the value out of temp1, and it produces a value in temp2. And then the actual store to the field consumes the value in temp1. So this way of introducing a set of dependencies lets us express the constraints between these operations in a form that the optimizing compiler is able to deal with, because it already has to know about the dependencies between different data accesses when considering whether or not to move code within a method. And so if we're going to move the store to PA, the loop invariant store, then we have to move all the things that depends on, which in this case would be temp2, which is the logging operation, which in turn depends on open for update. So we could do a transformation that's going to pull all of those out, maybe pulling the open for update and the 2 log for undos and the store to the loop invariant field, and just leaving the genuinely the code genuinely dependent on the loop iteration with the individual logging operation there. So we add these temporary variables during compilation, and then just before we generate the native code from this, we can strip these out again. We don't have to allocate a processor register to them, actually manage these values. They're just there to express the data dependencies during compilation. The second difficulty that we have with integration between the STM system and the rest of the tool chain is how to handle the garbage collector, because we might have problems such as what happens if the garbage collector runs midway through a transaction and an object has been made unreachable by the work that transaction has done. Well, then at a later stage, the transaction gets rolled back. We need to make sure we don't end up with a dangling pointer, depending on how these operations get ordered. We might have contrived examples such as this, where we have lots of work going on inside a single atomic block. And so it might be quite reasonable to have a garbage collection be triggered within an atomic block. We don't want to have to force all of the atomic blocks, all of the transactions in the program to be aborted whenever the garbage collector kicks in, because that would mean that we could never execute a program like this. And it might be very contrived to have such a long loop running all in a transaction and doing conflict detection between this work and lots of other threads, doing millions of cycles of work that might have to be rolled back. But a more realistic example would be in a modern language runtime system with a concurrent garbage collector, where the concurrent collector is running all of the time in a dedicated thread. And of course, we need then to integrate that concurrent collection with the STM system. So if we've implemented it with the garbage collection framework in general, and hopefully that carries forward to systems such as a concurrent collector. Now, so I said the idea of aborting all transactions on garbage collection is not attractive because it means that long-running transactions will never be able to commit. And there's not really a precedence for features like that in a programming language. And equally, we don't want to just add all of the transactional logs to the root set of the garbage collector, because there could be lots of temporary data that's been allocated within a transaction, if it's long-running, that should be eligible for collection. So we'd like to be able to reclaim space that's used by any temporaries that are dead at the current point of a transaction. So the intuition that we followed is to consider two possible views for the heap, and to make sure that the garbage collector will retain an object if it's reachable in the world where transactions abort, and also if it's reachable in the world where transactions commit. And if we do a validation of all of the transactions before we start the collection, then that means we only have to consider these two views of the heap. We don't have to consider all of the different combinations of one transaction committing or another one committing. We can just consider the case of everything commits or everything aborts, because the validation will guarantee there's no conflicts between transactions, and there's at most one thread writing to any given object at a given time. So what we do is to do two passes over the heap with the collector. First of all, a normal pass where we consider what happens if all of the running transactions are able to continue and commit. And then a second pass where we look at what happens if all of the running transactions abort. So in the example here, we've got the dark arrows are showing normal references within the heap, and the light arrows are showing overwritten references that some concurrent transactions have been manipulating. So maybe there's a local variable root pointer here, and that makes this spine of the list reachable. And then there's other bits of the heap that have been manipulated by transactions, some of which are unreachable from the rest of the heap, others of which have become unreachable because of the updates transactions have done. So we start out by validating transactions, as I said, and rolling back any that have experienced conflicts already, and then performing a normal garbage collection using the state of the heap that the transactions have left it in. So in the normal terminology for GC, these dark objects are the ones that are reachable from the normal routes. There'll be some grey objects, which are ones that the collector is currently scanning, and then the white objects are ones that are not reachable so far. So we run the garbage collector as normal, and that identifies that the spine of the list is reachable. We then roll back all of the work of the current transactions. We keep the logs so that we're not actually aborting them. We're just undoing their effects temporarily, and then we'll restore again before we resume the threads. And we mark as grey any objects that have been updated by those transactions. So in this case, this was a black object before that we've updated by one of the transactions. So if the transactions were to be rolled back, this could become a root of some new piece of the heap that gets reachable again. And then we rerun the collection, tracing from those grey objects, marking everything that's reachable from them. So we know at this point that the spine of the list is reachable if the transactions all commit, and that if the transactions all abort, then this additional old version of the list at the top here would become reachable again, but the nodes down at the bottom are not going to be reachable. So we can reclaim those, then restore the heap, letting the transactions continue, and then let them execute onwards. There's a slight additional complication for finalizers in C# and in Java. And these are methods that execute when an object has got reclaimed by the garbage collection. So typically there's a thread that runs finalizers, and the garbage collector hands off to it a queue of finalizer methods to execute. So we could write an atomic block like this, where we allocate an object with a finalizer inside an atomic block. And then we look at what happens with this finalize method. Maybe it's going to do some output that's visible to the user. And the question here is what happens if that atomic block is attempted multiple times? Do we actually collect this object multiple times and potentially run this finalizer? Or is the rollback of the transaction going to stop the object from being finalizable, maybe in effect making it look like it was never allocated in the first place? And in this case, and in a lot of the other ones where there's ambiguity over the semantics, the principle we followed is that we want atomicity and isolation. So if the programmer wrote that atomic block that allocates an object with a finalizer, then the programmer should just think about that atomic block running once with atomicity and isolation. They shouldn't need to think about the runtime system trying it multiple times until it gets to commit. So we roll back the allocation of the object, and we don't run the finalizer on those tentatively allocated versions. So we just wrap up today by talking about the retry construct and how we go about building that from the a couple other things, but let me just continue with retry construct and how we'd build that over the kind of Bartok STM system that I've described. So here's a version of retry using a fairly short example. We've got a buffer that this thread is storing data into and setting a flag, and then the second thread is going to call retry if it sees that the buffer is not full before it consumes the data and clears the flag. So semantically, we want this atomic block to be delayed until this first one has executed. And for efficiency, we want to avoid spinning. So we want to block this thread until it sees the commit from the thread on the left-hand side. The way we support this is by adding a new primitive to the STM runtime system called wait transaction. And semantically, this is the same as aborting, but it's allowed to block the thread for a little time until another thread has committed an update to one of the objects that we've read from. So this is going to help us make the retry operation efficient by letting it block until someone commits an update to something it's read from. So no point in executing the consuming thread here until the producer has executed. Retry compiles into a call to wait tx. And as I said, semantically, this is equivalent to aborting the transaction. So wait tx is going to block for a little while and then raise the tx invalid or tx aborted exception, which will propagate outwards to here, and then we'll catch it and go around the loop a second time. The work within wait is going to actually deal with the rollback so that we've undone all the tentative work that the transaction has attempted. To implement this, conceptually we add another header word onto the object, and we use this to represent a queue of threads that are waiting on a change to the object's fields. Now in practice, there's techniques we pick up from other parts of the runtime system to avoid us needing to have this succession of extra fields taking up space in every object in the heap. So we try to allocate these extra words only in the case of objects that really need them. But to simplify the slides, I'll show these as separate, distinct header words in the heap. So we extend the header word with a wait list, and we extend every transactions record with a mutex and a condition variable that are going to be used to control waking and sleeping that transaction. So the thread that's running that consuming transaction, along with its normal logs for the locations it's read and written to, it's got a lock and a condition variable. Then in the wait transaction call, we use an atomic compare and swap to link this consuming thread onto a list of waiters on the object. And the thread is going to validate the transaction to make sure that it saw a consistent view of the objects and really should be going to sleep. And then it's going to sleep on the condition variable in its transaction record. Now when there's a commit operation, that commit is going to, in addition to updating the version number in the objects that it's updated, it's going to check whether there's a non-empty list of waiters hanging on the object header. And if there is a list of waiters, it's going to lock each of these in turn and signal its condition variable. So that's going to do the support for blocking that we need. We'll be delaying the consumer thread until someone's made an update to one of the objects that it was dependent on. And it's then going to be woken via this condition variable that we have in its transaction record. In practice, the technique we use for managing these header words is based on the thin locks idea from many JVM implementations. We start out by not having additional header words on the object, and only when we access an object inside a transaction do we add space for the version number, and only when we block on an object using retry do we add space for the wait list. In practice, rather than just having a single link here, we need a doubly linked list that we thread through the transaction records. And the reason for doing that is because we might have multiple threads waiting on multiple objects and multiple objects being waited on by the same thread. So we need a slightly more complex linked structure to associate these, but I'll just use a single one here to keep the slide simpler. Now, the last topic I'll talk about is just one aspect of how we need to ensure isolation. And the particular problem here is one known as zombie transactions, which are ones that have experienced the conflict but not yet detected it. And we need to be careful about zombie transactions because they might do all kinds of things that reveal themselves. So, for example, they might enter an infinite loop depending on the state of values that they see. If we're using lazy conflict detection, never get to that final step at the end of the transaction where they do validation. So the particular problem here is, for example, we've got two transactions running in different threads. The one on the left is running an atomic block that reads from two fields out of an object, and then if the values differ, enters a loop. And the one on the right makes updates to both of those fields, storing the same value in each. So let's imagine that all of the threads in the system are maintaining an invariant that A and B hold the same values. And because the programmer just ought to think about atomicity and isolation, this is a perfectly reasonable thing for them to write, because the transactions running in isolation with atomicity are not going to see a distinct set of values in A and B, so this endless loop should never happen. But with the runtime system and the compiler that I've been describing, it's possible for this to go wrong, because it could be that we read from A here, then there's a context switch, and we run this second transaction in its entirety, and then switch back to A again and read from B. So maybe the two threads start out at 0, and we read from the two fields, and then we read from the fields again, and we'll end up with seeing 0 for A and 100 for B, see the values differ, and so enter the loop. So that will be an incorrect thing for the runtime system to do. Yes? So the question is, these are supposed to be atomic blocks, so there shouldn't be a context switch in the middle. And the problem here is we want to build atomic blocks with the semantics that they're atomic, but this is really fixing a bug in the implementation that I've described so far. It's one of the areas where the lack of atomicity in the basic implementation is revealed. So one option, as you say, would be when making a context switch to maybe to validate the transaction before continuing, or to go back to the start and re-execute it. But the problem then is, if we actually had a multi-processor machine, we might be running these on different processors, and it could just be that because of the non-deterministic timings of the machine, maybe this processor is interrupted for some other task when this second processor runs the transaction on concurrently with it. So we need to handle this case in the runtime system and make sure that we detect this lack of atomicity in this case. And the approach we've taken with Bartok STM is to actually add another function to the runtime system API called validation tick, and to ensure that the compiler puts calls to this validation tick function in all of the places where looping is possible. And the idea is that this is going to guarantee that we'll do validation in addition to the commit time validation, and detect in this case that we're in this loop and we've got in the loop because we saw an inconsistent set of values for A and for B. So the compiler adds calls to validation tick into any loop or a combination of branches that could lead to looping. And we optimize the implementation of validation tick so it's as lightweight as possible while still guaranteeing that eventually it will notice a conflict and re-execute the transaction. So let me stop there for today. The topics I'm going to talk about in the next lecture are looking at some of the semantics of an STM system in more detail. So I kind of touched on some of that with this validation example at the end, that there's lots of ways in which the atomicity or isolation that we wish to provide can leak out of the system. A particular problem is what happens if we're doing I/O operations inside an atomic block and we want to write to the disk or read from the user. And a problem I touched on a few times, which is what happens if the program is reading from data and writing to it in transactions in one thread, but reading and writing to the data directly in a second thread. We need to sort out what the semantics for those operations should be and what we should do in the implementation to handle that. So in the next set of the TM lectures, I'll talk about some of those semantic questions. And then in the additional lecture, which I think is scheduled in between, I'll talk about some of the work we've been doing, quite unrelated to transactions, in the Barrelfish Research OS project on some of the language abstractions for programming multi-core systems in that very different setting. So a little bit about recent research in Barrelfish next, and then in the next TM lecture, more on the semantics and how we provide atomicity and isolation. Thank you.